Hello, my name is James Kubley. I'm a technical support specialist at Saratech, and I wanted to follow up on our last customer enablement session with a demonstration of some of the dynamic capabilities of Femap. We're going to look at linear transient and nonlinear transient, both direct analysis. So I've got here a basic model of a motor mounted to a couple brackets. Materials are just steel. It is a mostly hex mesh using the hex dominant mesher. No contact. All the nodes have been merged for contact here in this situation, just to simplify the analysis a little bit more. Constraints have already been added. It's fixed at the bolt holes there at the top. And so what we're going to do is we're going to apply a transient acceleration load to this model. I've already created a load curve for it. It is two different frequencies that are summed together, and that sum is multiplied by a third frequency to generate this load curve over a 3-second time period. The input or of time is multiplied by pi to help convert it to basically hertz. So every 1 second should give me 1 cycle. And so I can see that my frequency input as 5 hertz, 12 hertz, and 0.15 hertz. And we're going to apply that as an acceleration. Now remember, this is going to be the values here are going to be a multiplier to our acceleration load. So I'm exceeding the value of 1, so we'll see close to like 2. And then my acceleration load is going to be gravitational acceleration. So we're going to see up to about 2 Gs of acceleration load applied to this model. So real quickly, I'm going to copy the data here. We've got quite a few data points. And we're going to Femap here, and we're going to make ourselves a function. I'm going to call this our time-dependent acceleration. And we're going to go versus time. And I'm going to use the option, since I've copied it to clipboard, I'm going to paste from clipboard. And there we go. There is our dynamic load history here. Or, yeah. Cancel all that. So let's create our acceleration. We'll do a body load. We shall use a translational acceleration. 386.4. Everything should be in inches here, and we're going to use that table I've just created for it. And keep in mind the frequencies I did pick are related to the natural frequencies in the z direction here. There's modes around 3, 5, and 7, and 12. So we are close to some of those modes here, or around those. I know I've got 5 and 12, but they're not exactly the same. They're a little off. So with that, we've got the minimums of our model defined here. So let's go ahead and set up our analysis. Go to manage, and we're going to create a bunch of them. We're going to go through several different setups here. So we're going to go new, and we're going to call this linear transient, and I'm going to call it 0.1 seconds. And that's going to be right here, option 3 for the analysis type for linear transient. And I know my time step's a little large here to demonstrate one of the issues with linear static that you can run into, or not linear static, sorry, linear transient, and that it is time step size dependent. We're not going to make any changes here. Most everything here is going to be default. So we're just skipping through here. Notice that here we're set, solution type is set for direct. We're not using the modal. And here's where we get the time step size. So we've got 3 seconds. So we need, and we're doing a time step size of about 0.1. So what do we need? About 30 steps then for 3 seconds. Output interval, we're going to leave that blank, so we should get all the results. Again, we're not going to mess around with anything. No need for solution frequencies. That's for a different analysis types. We're not adding any particular damping to this model. Constraints, it's set for a fixed, loads or acceleration, and then we just basically get our final results, or the results that we want to look for. We'll click OK. We're going to do a new analysis here. We're going to just queue them all up. I'm going to call this one linear transient 0.01 seconds. Again, we're going with option 3. And next, we could have copied everything because all we needed to change was one setting, so we're going to skip through this pretty quickly. There we go. So this time we are an order of magnitude more. So we need 300 steps at 0.01 seconds. I'm going to use an output interview of 10, so we get roughly the same number of results as we did before. Click, click. Same constraints loads. It's going to load that by default. That's one of the only ones, and we're pretty much getting all the same results output request. Now we're going to set up the nonlinear transient. You're going to see that's not too different. Oh, we're already set for yes, nonlinear transient. Let me put the 0.1 seconds. We're going to give it the same handicap so we can see its behavior. Again, I'm not going to mess with most of the defaults here. Direct is going to be the default, and that's what we're looking for. You can see that the dynamics tab here is still here, but we've lost access to the transient time step interval. Not to worry about that because it's actually going to show up on a different tab. Okay, so here we are. Now we're getting control options here for our nonlinear part. See, we've got our convergence tolerances here that we can set for load and work. We could check displacement and add that, but displacement converges much easier than these other two, so the need for those two, or the need for displacement isn't really important because it usually always converges ahead of these two. So we're going to go with, again, 30 increments, 0.1, so that we get our 3 seconds of analysis time here. We're not going to see how the system responds after the acceleration loads are stopped. So we just want to see during the acceleration process. And we're going to change this to yes. And we're not going to skip any results for this particular method, or for this particular one. Again, boundary conditions, fixed, constraints, loads is acceleration. We'll move on. Select the results we want for. We'll select acceleration like the other one had, and just click OK. Now this time I'm going to demonstrate a copy, and then I'm going to edit this one real quickly. So that way I can change this name. I'm going to click OK, and we're going to go into, not there, nonlinear options. There we are. And we'll click edit because we want everything else the same. I'm going to change the increments or time steps, the number of time steps to 300. I'm going to drop down in order of magnitude and time step size, and we're going to adjust this up to 10 so we still get roughly the same number of results. And click OK. So there we are. We've got all of our analysis queued up. And at this point, I'd click Analyze Multiple. I'd select them all and click OK. But due to the time it would take to run these analysis, I've already got the results, and we're just going to skip over that. Okay, we're going to assume the analysis have finished. We've got the results here now to look at. But before we take a look at our results, I want to look at the results, or not the results, the log files here to demonstrate part of the challenges with running the linear versus the nonlinear analysis. So with the linear analysis here, we'll take a look at the F06 file here. We'll find there's not a whole lot of information as compared to the nonlinear analysis when it comes to how the analysis ran with each increment. There's none of that convergence criteria that it was looking for, so there's not much in here. But let's keep in mind that but to see how quickly it ran, let's take a look at this log file. Scroll down to the bottom here. This took 5 minutes to run. So very quick. If we go over to the 0.1 seconds, or 0.01 seconds, again, doesn't tell us anything particularly different in the analysis of how it might have ran as compared to what the nonlinear is going to show us. We take a look at the log. We can see that it took 28 minutes to run 300 increments. Now let's take a look at the nonlinear. So our first one, the 0.1 seconds, we'll take a look here at the log, and we get much more information. We can see here as it marches through time, it outputs our convergence criteria, the number of iterations it took, and if it had to do any sort of bisecting of the load curve. So as you can see here, we start off with the 0.01, the 0.02, but then it's got to make an adjustment, some additional adjustments, and from there we don't quite get the same time increments as we had originally asked for. We'll go through it. There's a lot of data here for 3 seconds. You can see it kind of struggled to run this analysis at that a bit of an oversized time seconds, or oversized time step size. Again, that was by intent. If we take a look here at the analysis time, it took 8 hours to run that model at that larger time step size. So the nonlinear transient is very time consuming. That's the reason why it's best for small or short events. So here we go to the smaller time step size, the 0.01 seconds. It appears to have ran following our iterations pretty well. So you can see just about 2 iterations on average. Then it kind of climbed up, struggled a little bit. We had some change in analysis time step size before it was able to fully run. You can see, we'll scroll through here. You can You see it took a lot of work to get this model to run. And let's take a look at that log. "14 hours for this model to run at that time step size, 300 increments at 0.01 seconds. Took 14 hours, almost 15. So let's take a look at our model here. We could look at the results here if you like. We could see displacements at any sort of time that we want. We've got our displacements, or display shaped, contours, but it really isn't going to help us compare these models too well. So a chart here would probably be the best example. We could plot the displacement of one of the nodes here versus time, and you can compare all 4 series at once. So we're going to go with new data series. I'm going to title this one Linear Static 0.1 seconds. I'm going to change this to vector versus set. Output set value. We don't want to use all the output sets, but we can use this study here. So we're going to go linear transient study. I'm going to change this to T3 translation. Our load was in the T3 or Z direction, and our location here, we should just be able to pick that, not U. Let's go with our chart is a bit large here and in the way. Hold on. There we go. Sorry, new data series. Let's go. Linear transient 0.1 seconds. Vector versus set. I'm going to look at the output set value. Deselect all output sets so we can select our particular set of results. So we got linear transient, T3 translation, and let's select a node about roughly right here. I'm going to copy and paste this node so I don't have to select it every time, and go OK. Dialog box has popped up again. We're going to change this one to the 0.01 seconds. Linear transient, and it's kept our location. Everything else looks good. We're going to go OK. Our graph is starting to look a bit messy now. We'll be able to use another tool to help us visualize a little better. But we can see right now our 2 linear transient analyses have given us 2 completely different set of results based off of the time step size. And then let's call this nonlinear with the 0.1 seconds. Same location, same results. We'll click OK. There we go. We're getting all these intermediate results. We get a bit smoother of a plot, but again, it differs from the other 2. And now let's do the finer time step size here. And we'll click OK. Now we've got kind of a mess with 4 overlapping plots here. We'll click cancel. And now we've got this. I'm going to click done just for a moment because I want to expand our chart a little bit here. And let's go back into it. And we're going to enable highlighting here. So we've got, it's a little easier to see, but it now looks like our nonlinear transient is giving us results more closely assembling or resembling the linear transient with the finer step size. So we're going to enable highlighting. So hopefully this yellow contrasts very well for your viewing screen. So now we're looking at the nonlinear transient extending out here. Our results are a little choppy because I had a number of increments to output. If I left that blank, we would have all the little intermediate struggling results where it had struggled to converge a little bit. But you'll notice here that our two nonlinear transients, even though it's tracking convergence, did give us two different results here. And that's because even though we converged on the nonlinear transient result with the larger time step size, we didn't converge on reality. So time step size can still play a part in a nonlinear transient. You got to keep that in mind. And this is kind of an extreme example because if you look at our loading conditions, 0.1 just doesn't match appropriately. But the 0.01 seconds is a little closer. And because it had to take smaller time steps, our results here are more likely to be appropriate for for what we're looking for. But if we compare that nonlinear transient to the linear transient, they look nearly identical. The problem is we can sort of see these peaks are a slightly bit different at some points. It could just be where our data points are at, but if we take a look over here, we've got some a bit unique responses here that don't quite match up with the between the two. So more on the right hand side, we'll see the way it has changed. So, but yeah, here's the linear transient. Just kind of looks like noise. Definitely too few data points. The nonlinear transient, you would think that we had we did have too large of a time step size, but you think that would affect our results, and it did. And you would think that would affect convergence. While it did affect the ability to converge in a smaller increment, it did manage to still converge and run the analysis to conclusion, but still give us completely different results. So real quickly, last bit I want to do is just compare that linear transient to that nonlinear transient with the smaller time step size. So I'm going to delete our two other plots. So we're not seeing so much noise or so much overlapping data. All right. Not the best of colors. Let's go in and change that. Let's give that a nice kind of purplish color. And we'll give this one a different color. Let's give that how about just go with a black color. It won't actually apply these until I click done. There we go. Hopefully that stands out better on your screen. You can see, so you can see here the two do track fairly close to begin with. We get some of the more excitable situations here. The linear transient underestimates some of this, whereas our nonlinear transients gives us a higher peak result at some points. But they do mostly stay in phase with each other until we get over here. And then we're kind of out of phase with a few of the results. And then our amplitudes are a bit off. So yeah, keep that in mind. Time step size is important, highly important in a linear transient, and scarily important in a nonlinear transient, because you could still converge on results and think that you have a fine enough time step size. But again, thank you for joining us for our CES event, and thank you for following up with this demonstration of the linear versus the nonlinear transient.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.